Someone suggested I make a video on kinematics graphing, especially helping you with 11 kinematics graphing exercises. So before we start, let's just review and make sure that we have our basics. I want you to write down the equations that would explain the difference between, explain these terms: displacement, average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. See if you can write down the equations that you would use to explain those terms if I asked you to explain them on a quiz. So pause the video and try to do it from memory, and if not, you can look them up, but you want to understand them. So do the best you can from memory first. Okay, this is what you should have written. This is all on your equation sheet, but you don't want to just rely on your equation sheet when you need it. You want to understand these concepts. You want to internalize the understanding of these concepts. So displacement is simply the difference in two positions, and it can be positive or negative. So you take the final position and subtract the initial position. Now we write it in X, but we can write it in Y. It doesn't matter. And in 2 weeks, we'll deal with displacements in two directions where you'll have a delta X and a delta Y. So the change in position, and then average velocity simply becomes the change in position. Whoops, that's a mistake. Change in position over change in time. Oops, there's still a mistake. I jumped ahead to acceleration. So that's average velocity. And we know what that is, right? We let the cart go down the track. We measure the total distance in total time. We get the average velocity. But if the velocity is changing, the average and the instantaneous aren't going to be the same thing. So we think of instantaneous velocity as the velocity in an instant. To get the velocity in an instant, which is the rate of change of position with respect to time, we have to do a small delta x and a small delta t. And in the limit as t goes to 0, that is the derivative of x with respect to t. So to really define instantaneous velocity, we need calculus. But in the lab, what does it mean? You got to measure a small distance in a small time. That's why we use the photo gate or the ticker timer or the motion sensor, right? And then similarly, acceleration is a change in velocity over time. And if the acceleration's changing, which it doesn't on a flat track, but it would on a curved track, right? The acceleration would have to be defined as the acceleration measured over a small time interval, which in calculus would be dv dt, or if you haven't gotten there yet, since v is the derivative of x with respect to time, this is the second derivative of the position vector with respect to time. So it's important to know displacement, velocity, and acceleration, and be able to distinguish between average and instantaneous. Okay, one more thing before we start the graphing. From these equations, we derived 4 working kinematics equations. They're on your equation sheet. Write those down just for practice. These are our 4 working equations for kinematics. We're going to use them a lot. It's important to know that these are only good when the acceleration is constant. When the acceleration is constant, then the average and the instantaneous acceleration are the same thing. So we take our definition of acceleration and we rewrite it. V final equals B initial plus AT. It's just a rewrite of the definition. That's our first equation. Then we take the average velocity equation and we rewrite it that the distance you travel will be your average velocity times your time. But here, for the average velocity, since the acceleration is constant, we take v final plus v initial over 2, right? That's the average velocity times the time. And with these two equations, as I showed you in the last video, if you take V final and you substitute it in here and do the algebra, you'll get this equation. This equation we use a lot. And you'll see we'll use it in this video to find displacements when we know the acceleration and the time. And in other cases, sometimes we might know the velocities. We might be looking for the acceleration when we know the final initial velocity and the distance, but we don't have the time. Equation 4 is useful. That comes from solving this for time and substituting it in here and getting this equation. So these are our 4 equations, and we're going to save those as we begin talking about graphs. So here's a familiar situation, a cart rolling down a ramp at a certain angle. We did it in lab. And one way of understanding or visualizing this motion is to graph it. And there's 3 different graphs we could do. We could graph the position versus time. We could graph its velocity versus time, or we could graph its acceleration versus time. So pause the video and see if you can guess what those graphs are going to look like before we actually dig into the details. Sketch out what you think the graph is going to look like, and it's better to guess than to just sit there scratching your head. Make a guess. If you're wrong, that's fine. At least you're thinking. So what you should know is the acceleration of that cart depends on the angle, right? The steeper the angle, the greater acceleration. Since the angle is constant, acceleration is just going to be a straight line. It's going to be a constant value because the angle is constant. That's why we don't usually graph the acceleration. It's not very interesting. But since the acceleration is constant, that means the velocity is constantly increasing. So the velocity, assuming you start at rest, is going to be a straight line. Now, as the ramp is more shallow, the velocity will increase slower. As the ramp gets steeper, the velocity will increase at a greater rate. And since the acceleration is the derivative of the velocity with respect to time, which is the slope of the line, we can see that the slope, we use that in method 4 with the motion sensor, right? We can see that the slope of this line is the acceleration of this. So if that were this would have a higher acceleration, and so on. Since the velocity is constantly increasing, that means the amount of distance that the cart covers is going to be small in the beginning, and as the velocity increases, it grows, and so the shape of this graph is a parabola. And you could see that in the equation number 3. Look at equation number 3. Delta x equals Vx initial t plus 1/2 the acceleration times the time squared. That third equation, the initial velocity is 0, so the x is 1/2 axt squared. That is, right, the function that graphs a parabola. Now, another way of visualizing, now in order to graph this we need data. So what do? We hook the cart up to the ticker and we gather a bunch of numbers, right? So let's do that. Let's see what actually, let's start with this. I'm going to give you this. Supposing method 1, remember method 1 in the lab, supposing this cart goes 60 centimeters in 1 second. Find the acceleration. That's method 1, right? We just measured the distance and the time. So pause the video and try to do it from memory. Don't go back and look at the lab. See if you can figure out, given the distance and the time, how you're going to get the acceleration. This is good prep for the quiz. Okay, I hope you remember what we do is we find V average. That's easy, right? 60 centimeters in 1 second. That's 60 centimeters per second. And then since V initial is 0, V final is going to be double that, right? Because V final plus V initial over 2 is V average, right? You should understand all this. And so V final is 120. And then, this is getting a mess, but the acceleration is V final, 120 centimeters per second, minus V initial, 0 centimeters per second over 1 second. It's pretty simple, 1 second. And so you have that the acceleration is 120 centimeters per second, or centimeters per second squared. So if we were graphing this, this would be at 120. Okay, now use that. Now, well, we could use that and our kinematics equations to find the position every 1/10 of a second, and then we could do the graph, right? But let's use the ticker timer. Let's use this ticker timer, and I'm going to take the ticker timer and show you what we get. So here's the ticker tape, and it's kind of hard for me to draw this exactly, but this is, notice that the intervals are getting bigger and bigger and bigger as it goes down. Here are the measurements. So in the first second it went 0.6 centimeters, and then it went from the end 2.4 centimeters. These are the total distances all the way down to 60. Those are 10 numbers, and now we want to graph that. So sketch the graph of that. Actually on a piece of paper with a pencil, sketch that graph. Anyway, granted, not that easy to do without a piece of graph paper, but you can see if you sketch out a scale, it's going to be a parabola. And if we did it with a piece of graph paper carefully, or we gave it to a graphing program, it would sketch out a nice parabola. Now notice, how are we going to calculate, in order to graph velocity versus time, we're going to have to get the velocities. Now watch, let's just do V final, like the way we did it in lab. The last interval, notice, it's going 11.4 centimeters in 0.1 seconds. That would give us 114 centimeters per second. But we already know, if you remember from the previous thing, it's supposed to be 120 centimeters per second. So what's wrong? Well, what's wrong is this is the 1/10 of a second is too big an interval, so it's close but not exact. So one way we could get those numbers is to use the acceleration. So let's use the equation that V final, or V at any point, is V initial, which is 0, plus AT. So use that to generate the 10 velocities that we're going to get between 0 and 10 seconds. Get those 10 numbers and then come back. So there are the numbers. The equation, right? V equals the acceleration times the time, 120 times the 1/10 of a second, 2/10, 3/10, 4/10, all the way up to 1 second. And now if we graph this, it's simply going to be a straight line, right? If we do 10 intervals, each one is 12, 24, 36, right? It's going to be a straight line. And the slope of that line be 120 centimeters per second. So one of the things to notice is that the velocity is the slope. So if we take the slope of position versus time, we get 0 in the beginning, and then we get 12, and then we take the slope and we get 24, and we get 36, and so you can see that the slope, which is the tangent to the curve, remember that, is constantly increasing over this parabola. And so the slope of this is dx dt, and that is the velocity. But it's hard to actually get it by measuring the slope, so we use this to calculate the numbers. And the slope of this line is the acceleration, which is constant. Okay, let me give you a couple other things to think about. Actually, I changed my mind. Here's another example. Here's a ball, and I'm going to throw it up. It's going to reach the peak and fall. And what I didn't do, so when an object, we're going to learn this in a couple weeks, when an object is in free fall or just thrown, whether it's going up or down, it's subject to the acceleration due to gravity, which is 9.8 meters per second squared. But in many cases, in the Minds on Physics exercises, just for the simplicity of the math, we'll use 10 meters per second squared. And actually that should be negative because it's down. So with that in mind, let's study this situation where I throw the ball up. Well, I don't think I can throw it this fast, but I throw it up with an initial speed of 40 meters per second. So since we know that the acceleration is a negative 10 meters per second, what we know is after 1 second, it's going to be 30 meters per second. 2 seconds later, it will have dropped by another 10 meters per second, so it'll be 20 centimeters per second, 10, 0, and then it will come back down negative 10, I didn't write that, negative 20, negative 30, and 1, 2, 3, 4, 5, 6, 7, 8 seconds later, I'll catch the ball coming down at a speed of 40 meters per second. Now what I did was I used the kinematics equations, right? Those 4 equations. You can use this to calculate, either one of these to calculate the delta x. This is really a delta y. And these are the numbers I got. So in the first second, it goes up 35 meters. In the next second, right, it's slowing down. So it only went up another 25 meters to 60. It's slowing down. Now it only increased 15 to 75, and then it increased 5 to 80. And then from 80, it comes back down, going faster and faster, and matches these positions coming down so that after 8 seconds it's back where it started. Okay, so use these numbers to graph position versus time and velocity versus time. Do that on a piece of paper, draw it large, and sketch the position versus time and the velocity versus time graphs for this motion. Okay, I hope you did that. So here's at 0, and then 1 second later it's at 35, then it's at 60, then 75, then 80. And you see it comes down. This isn't a perfect graph, but you can see since it goes up and down, this is a parabola. And notice the parabola is pointing down. That's an indication that the acceleration is constant. But this is different from the other graph, right? So the slope, right, is getting less and less and less. And at the top, the slope is 0. And the velocity 0. So now graph the velocity versus time graph. Okay, I didn't warn you, but there are negative velocities, right? As it's coming back down, the velocities are negative. So notice it's 40, then it goes to 30, then it goes to 20, then it goes to 10, then it goes to 0, negative 10, negative 20, negative 30, negative 40. So you see that even though it passes through 0, the slope of this line is constant. And what is the slope of the line? It's a negative 10 meters per second squared, because the slope is the acceleration. Okay, so that concludes our overview of kinematics from a graphing perspective.